Everyone. I hope you are also staying sane in all of this craziness, and I hope you are spending maybe productive and or at least healthy, mentally healthy times. I just have this presentation for today. I hope it's not going to be too long, but the thing is that this presentation is actually just kind of a collection of, I would say, tips and tricks for developing deep learning products in practice. This is has been like kind of collected from different advices, from kind of my previous experience as working as a machine learning engineer in one of the companies or startups before, and from my working now with Unity 3D technologies, and also some advices from other colleagues. So it's kind of described as, I can describe it as a cocktail. And that means there is no specific thing I want to cover, but it's kind of chunks, small chunks from a bit of advices that I think it's important when you are trying to develop deep learning models, okay? Or we can generalize this for many of the data science projects that involve deep learning. So I will also recommend that we do the session in an interactive way. If you have a question or something, you can just post it in the chat or unmute yourself and speak, and then we will interact with each other. Okay, so the first bit of concern that we have is that machine learning is a unique deployment problem. We, for example, here at AMMI, usually we have notebooks to work with. If we start working with any task, probably there is a data set that is clean, organized, or it's not that kind of dirty. It's kind of somehow different from the reality when you're working with real projects, where you spend sometimes around 50 to 60% of your time in things that doesn't involve the state-of-the-art models. And that's kind of annoying for most of the people who works in the industry. That's why also a lot of the people try to stick to the academia, because of the extra headache or the burden that they're gonna have in the industry when they're working with real data and real products. So there is the most common way machine learning gets deployed today is in PowerPoint slides. It's easy to talk about machine learning in PowerPoint, but when it comes to reality, it's usually a big failure. Less than 5% of the commercial data science projects make it to production. So that's another aspect. You would see a lot of the data science teams, a lot of the hiring happening here and there, but that's just because the companies are trying to get kind of a lead over the other industries for their projects in the R&D sections, but still they're investing a lot of money, and 5% of these projects are only making it to the production. And it's hard because there's many constraints to make these data science projects or the deep learning projects that we make useful for the industrial applications. And because there are many constraints that usually we don't take into our minds when we are doing the same kind of projects in academia or research paradigm, because there are many imposed constraints by the scalability, the inference time, for example, or the network bandwidth, and some of the things that you would never think about in advance. So that's what makes it harder to be a successful machine learning project. I would specifically start talking about neural networks. And this is kind of part of chunks also from the article Debugging Neural Networks that I have it on the references. So why would it fail when we are usually using neural networks? One of the main reasons is that neural network training is a leaky abstraction. So usually most of the developers out there who are coming from software background, they usually would use something like this, like your data is something, plug your awesome data set here, and the model is super cross validator, and then super duper dot fit your data, and then send ResNet 50, and then SGD optimizer, and that's it. And we think it's gonna work, but in reality, it's going to be like a big failure most of the times, unless you have luck. And this leaky abstraction is because now these simpler abstraction, like provided by Keras or PyTorch Lightning or any kind of other frameworks nowadays, which is adopted by the majority of the developers, are providing like kind of abstraction that doesn't tell you what's going on under the hood. And at the same time, you unless you know what is the real implementation or the real components that got abstracted in this lion, nothing will work fine. Okay, so it looks like a courteous developer has taken the burden of understanding the underlying complexity for us, and this is kind of appealing. Yes, we want to do something like this to be productive, but at the same time, this is one of the major failure components. Okay. So we will come into this again, but I'm just talking about these reasons or potential reasons. The other thing is that neural network training fails silently. It's not like software components that you can test easily, and then you perform unit tests, and then you have a lot of teams that they approve merge request into GitHub repository, and then they perform integrated tests and so on. It's not like that. Usually you don't know what's the main reason why the neural network is failing, and fails silently because it could like seems it working, but is actually there is kind of thing is preventing the network of like it could be very small sneaky error that prevents your network from performing much better. Okay, so everything could be correct syntactically, but the whole thing isn't arranged properly, and it's really hard to tell or unit test because the possible error surface is much larger and logical as opposed to the syntactic. So it's the possible error surface, I mean, like many things could go wrong, and in the same time, the kind of errors, you could not easily catch them syntactically. It's not like kind of string that you have sent in a state integer, or it could be that, for example, a function expected a sequence of this length, and then you send that one. So usually neural network, because they are treated as a universal function approximators, they would work with any kind of data representation that you're working with, and the error surface will include the syntactic errors as well as the logical errors in the same time. And these logical errors are much harder to detect than syntactic errors, which is in the case of the software projects. Okay. So we will start about maybe kind of a recipe of training neural networks. This is not done by me. I will send you the article, for the great article that I would recommend everyone to read it. But let's just go through the steps. So debugging neural network, this is the two general advices. Start from simple to complex. And at every time step of the way, we make concrete hypotheses about what will happen. So in any kind of thing. So there is many moving parts when you're developing neural networks. try every time to have just one part moving at a time. So there's many moving parts, and if you move all of them, you would not know what to expect. So you moving one part, so you could have a concrete hypothesis. Still, it's a hypothesis. Yes, it could be wrong or right, but at least you could test the output for one possible input. Okay, and then you can diagnose that as you go up. This is the same advice, but just rephrased. Avoid introducing a lot of unverified complexity at once, which bound to introduce bugs, misconfiguration that will take forever to find. So especially if you're working with research, regardless if you're building product or not, it's always tempting, the idea of adding many complexity items. It's like, oh, I think we should build better representations for this by embedding, for example, another embedding layer on top of this embedding layer. Or let's just maybe add 2 layers instead of 1, and so on. So it's always tempting to add complexity, because there's many approaches that they have proven to work in many different tasks, and there is no just one right approach. And this is another problem, because there is no one right approach. You would sometimes try to take a hybrid solutions and then combine them together, and this would be potential failure, or it's not potential failure, but it's just like you're trying to cook a recipe that you will never know what will be the output of that. Okay, so this is the other thing. So to avoid this, we will just go through some of the steps, okay? And we will go from the data pipeline, development pipeline, and then we go to the deployment and scaling pipeline, okay? So for the data pipeline, it's usually in when you're doing projects that already have been done by people before you, or kind of Kaggle competition that already have these competition have their own kernels, or other people data sets that is already clean. You usually don't feel the burden of having data first approach. Data first approach means like you spend considerable amount of time understanding the data. And I know many of the lecturers or colleagues, or even if you worked before in any kind of project, it's important to work with data, but no matter how we stress on this point, it's still gonna be more important than it really is. So inspect the data, get intuition about the complexity of the task you are trying to achieve. So you're human, you still have your mind. You don't have to throw it to a black box from the beginning. Try to do data analysis. So usually we don't have a very good course about data analysis and exploration in AMMI, and we still do basic data analysis techniques. There are some of the courses that talks about, for example, mutual information and correlation and so on, but still these are not the kind of way that you're trying to explore the data or visualize the data in a way that you can decide what to do, and at least to get sense of the complexity of the task. So you could have like large amount of data, but the task is very complex. You could, for example, let's take the Cassava challenge that you were working on. You could inspect, for example, the leaves by your visual inspection, and you could compare the different kind of diseases by yourself and try to see if you are, as a human, are you capable of distinguishing between the different diseases themselves? Are you noticing any patterns between the leaves? So that could actually change a lot of the decisions that you might take. Am I going to undersample the image? If I shrink the resolution, do you think I will lose kind of features that will help discriminate between the different images or not? So it's not only to understand the data, but it's also crucial to make decisions about the approach you are talking, you are going to take to solve the problem. Okay, um, give it time, understand the distribution, observe the patterns, and notice their statistical properties. So this is, everyone is saying this. Clean the data. So usually we still, most of the projects that we've worked on is still the data is clean, but especially if you're working on a novel domain, you're not just gonna try your data set on a toy, your model on a toy data set like MNest or CFAR or even ImageNet that is already have good transformations, and the labeling is guaranteed to be like kind of a high quality and so on. So usually if you are working with a different domain, let's say you're working with a genome sequencing or fintech data time series or anything, usually you would find a very dirty data, and this is really kind of one of the big burdens. You want to look at the outliers, you want to look at the nans or where the corrupted data, look at the data types if there is conflict. It's kind of not pleasing work for something who was doing research, but you would not actually get your research to get succeed without having clean data, because you're going to build a lot of assumptions which cannot be verified unless you are working with ideally assumed data. Over under sample unbalanced data, we will talk about the unbalanced data later. And then you're gonna also look at the features. So you could look at the scales of them. Do I need to downsample some of, for example, images? How much variation do I have in within the classes themselves? And is there any kind of spatial temporal properties? So I could maybe, if there is a spatial properties, even if it's not images, I could use CNN architectures. If there is time, I could arrange the data in a time series manner, even if it's not actually time, like arranged in a time series manner. And that's kind of a button. This, for example, could change your entire approach from going into solution A to solution B. Okay, so so usually now, for example, I'm working as a data scientist. There are data engineers who usually do this kind of data for us, but the data engineers are not doing this separately from what we as data scientists do. We sit with the data engineers, we discuss what is actually going on with the data, what kind of feature engineering we need, what kind of validation, and so on we are looking for. So there is a kind of a pipeline that is kind of unified among different kind of roles between data scientists, data engineers, machine learning engineers, business intelligence specialists, and so on. All of them are doing this kind of a step about extract, transform, load, the ETL concept. If you ever heard about it, it's that, let's say we have, you're working on Google, we're working on a company that have multiple servers. It doesn't have to be the size of Google, but you could have multiple sources. You aggregate these sources or data from their sources. It could be data from sensors, data from databases, data from points of sales, whatever kind of the sources. It's going to be different sources, and they're going to be in a different format. So when you pull them from the sources, you're gonna build kind of like a layer of that is just functioning on, or its target is just to extract these data from the sources. And this layer is the extract layer. And then we have the T, which stands for the transform. Because these data comes from different sources, there is no guarantee that they're gonna have the same format. But we want, for example, if we want to process this data or build models on them, we want to make sure that they are having the same format. That's why you're gonna build another layer. This layer is not like a neural network layer, it's just kind of a software component that someone is going to build. If you're working with a small company, usually data scientists are involved in this. Usually and then bigger companies, usually either the business intelligence specialists or the data engineers are responsible from this. But usually it's a good idea to have maybe a rough idea about what is going on in the process before you come and train your model on it. Then you are trying to load this data into unified data set. So architecture, which is called the data warehouses. So you have a data warehouses locally, you aggregate the data, transform them in a way that they are valid to sit maybe in SQL databases, relational databases, no SQL databases, whatever kind of format they are stored in. This is the load step, okay? So after this load step, usually if you have a stream of data, let's say you're working on Facebook and you're working with the marketing team and you want to try to analyze maybe the behavior of users or do kind of customer segmentation or whatever of this, usually we'll have a stream of data that you're going to pull every day or maybe on a frequency of days. And usually you'd have corrupted data because the ETL itself, it could have maybe kind of bugs that would not guarantee that you always have the same format or you will have the same kind of data. Or maybe you would have moving sources. So sometimes you're gonna pull from this data center, sometimes you're gonna pull from the other data center, or so on. So there's no guarantee that the model that you will build will always have the same kind of data as input every day. And that's why comes another layer after the ETL, which is the validation layer. So the validation layer, this is a diagram from the TensorFlow data validation module. So this is, okay, let me see, where is it? Yeah, so I guess I skipped one slide. Yeah, this slide here. So the data validation schema. So usually, if you want to have if you want to make sure that the data that you have in your data warehouse after you did the ATL, it's going to be the same as in day 2, day 3, and every day, and then you're going to send all of these data to the training. But you are not sure that in day 2 you will get the same data in day 1. What you would do, like a kind of a solution from engineering perspective, if you could suggest anyone? I would think naively, maybe on building a script to check the data here. This script should generate maybe statistics and look about maybe the mean of every feature that I'm looking at. If there is any outliers, if there is any nans, corrupted files, or whatever, because it could be anything. It doesn't have to be a relational data set. It could be images. It could be any kind of data you're working on. So this is kind of need a lot of time to work. Or at least effort to write these scripts, because this script need to ensure everything that is correct. There is just one example. I'm just talking about this tool, which is or module, which is the data validation in TensorFlow schema. This is just one example of how we can automate this process. If you have the data set, you could clean it one day on day 1, and then you can generate the statistics. Let's say we have feature 1 relies on this range, and it does have this mean, and this is standard deviation, and it does have this data type, and so on. So you validated this data set, and you expecting the other data sets or the other days will have the same kind of features as the same one on the first one. So to do so, usually either we hard code these things. You take the statistics from this one, and then you hard code it and write a script to validate it for the other days, or use, for example, TensorFlow validation, which is actually it will use kind of heuristic to infer the statistics and to infer the metadata from this data set. And then when you have a new data on day 2, you could use the metadata that has been generated here. This metadata, you could call it schema, okay, or inference schema. So we're gonna infer the schema. There is algorithm that is designed by TensorFlow guys that they're gonna infer what kind of data types, range, mean, standard deviation, or all of the statistical properties of the data that you're gonna be working on. And then you're gonna save that as reference schema. And then you're gonna use this schema easily to validate the other upcoming data on the upcoming days without writing any kind of scripts or having all this pipeline of validation. And this could be done with 2 lines of code in TensorFlow, but I'm not gonna go through it now. It's just an example of an idea how we would have a pipeline for the data. We extract, we transform, we load, and then we validate before we feed the data to the model. And the validation include the kind of transformation that we usually perform, which could be feature scaling, normalization, or anything of data. And this is kind of, will take us a long time to discuss the non-zero centered activation, but it's just a bit of advice, unless you have like a clear reason about why you want to do feature scaling over feature normalization, it's better to do feature normalization. Because with normalization, usually if you normalize it around, that depends on the normalization itself also. So if you normalize it between, for example, -1 and 1, you would have a better degree of freedom in moving on the landscape of the optimization, and that will converge the optimization faster than having, for example, normalization between 0 and 1, or scaling between 0 and 1. And I don't want to go into this example, but I will send you a video that explains the idea from the course that you have taken with Georgia, or it's the Johnson from Michigan University. But that's going to take a lot. I need actually some graph to illustrate the
Hello,
idea.
Mustafa.
Yeah.
Yes. So back to this image. Do you mean that we do some processing on the day 1 data and use that to validate the subsequent days data we have from that?
Well, sorry, can you repeat the question?
I mean, we have day 1 and we have the infer schema from there, and we use that to validate day 2, day 3, and the rest.
Yes. So this is, you see this schema. So infer schema, usually instead of you are trying to define the constraints that you want to have for the other data sets to match this one, there is one line of code that could get the schema for you in TensorFlow for the data set. So you give me the URL or the path or whatever the data set that you have, and they will try to get the schema. They are using kind of heuristics to infer this kind of schema. So you don't write any kind of script, and then you will use this schema to validate the other data for the upcoming days. So it's a one-time job. You clean this one.
Okay. Yeah, that's just what I wanted to know. That because the one data could potentially also have some noise and some nonce and the rest. So
yes, so you spend some time to make sure this is the ideal image that you want to have. But it's also they have good features on the TensorFlow validation module. Is that sometimes you wanna you know that, for example, in day 1, let's say the prices, it's you're working on a fintech, and then you had this data from the first quarter of the year, and you know, for example, the prices for certain commodities will be in a range that is usually lower from the other quarters in the year. So if these are coming from the other quarters, you would actually have the option to modify the schema manually, so it will still tell that the ranges that are coming here are valid, although they are not the same as in the first one. So you still can play with this manually before using it to validate the other schemas. And also at the same time, you could have the schema to be chosen to be used in a training mode or a serving mode or different kind of modes. So usually if you are doing training here, then you would use this schema maybe for the same purpose. If you are having a model that are used in a serving mode, which is just gonna do inference without training, then you would have maybe a slightly different version of the schema, and that just could be also changed with a few lines of configuration. I could send that for the tutorial, but I don't want to dive into the details here or the technical details. Okay, so let's go for the development pipeline. After we spend some time with the data, understood it, and then we will start with the development. Here where the things get ugly, okay? At this stage, it's best to pick some simple model that you couldn't possibly have screwed up somehow, a linear classifier, or a very tiny component. You will want to train it, visualize the losses, and any other kind of metrics, accuracy, model prediction, and so on. So that's especially, for example, if you're working with PyTorch and you're going to build your optimizer, optimizer.step, and training function, and test function, and then the entire pipeline. So usually just pick a TOEI model or a simple model in the beginning. And this is not because you want to start from this simple model, but just this model at least can ensure that there is input going on, there is output, I can differentiate, get gradients, get update, and then move the pipeline as I go, okay? So first start with a very simple model, just to verify that the pipeline for the training and the evaluation skeleton is there. Avoid random initialization variations. So usually people are talking about the reproducibility in neural networks, but most of the people, if your results are not robust across different random seeds, then your model is not robust enough to generalize well, okay? That is true. But when you are developing projects, don't misunderstand that we don't want to fix the random seed. No, actually you need to fix any random seed when you are developing, because you want to at first get insight about what is working and what is not working. And if you are having very complex landscape that have many local minimas, you usually could go to very maybe premature conclusions about your model. So the idea is that fix the random seeds at the beginning, but then after you get an idea about your hypothesis, like if I added a layer, what will happen? You need to fix the random seed at least to start from the same initial conditions or initial points, so you can compare them. If you're starting from different random seed at each time, or the optimization landscape, you will not be able to judge if your change is actually for the good or the bad. So this is during the development. After you finish the development, you could take the random seed off and try to see how your model is going to generalize. But if you don't fix it, the variation could drive you crazy, okay? Verify the initial losses. So you usually want to check if your losses are blowing up, or they are vanishing, or what's going on with the loss. So usually if you're doing classification, you would expect a random accuracy, which could be 1 over the number of classes. And then this is just to verify that the pipeline that you have built with a very simple model is still working, okay? Initialize well, incorporate priors such as Imbalance data sets. So usually the people sometimes play with the initialization. It's very rare that you find people these days trying to play with the initialization, although I recommend reading about the different initialization, like Xavier and the Microsoft initialization way of just having it's just you're gonna initialize the layers in a way that you are trying to maintain the variance that you will have across the activation in the layers. But unfortunately, that's a topic that we need maybe another time to explain, or we're just gonna send you videos to watch it. So you could play with the initialization. Usually, if you're doing PyTorch or TensorFlow, they're gonna use one of these default initialization, but especially in the recent years, for example, there is discoveries or papers that these even default initialization wouldn't work well. So an example, I don't want to go for that in details, is the variation. So the variation that you would have in the activation in each layer, if they are big, that means your gradients will not blow up or just be very small. And that is the target. But for example, in the skip connection, you will have another residual connection that will add the variance that have been shown in the previous or on the representation before the transformation, and we add it to the representation that is transformed, and this will actually add to the variation. So the variation will be doubled, and this is make it harder when you're trying to optimize and stabilize your neural network. So the default initialization techniques are not, still they are going to work, but we are talking about better initialization. So the initialization at the end will not harm your network as bad as, for example, bad optimization. But good initialization will help you to converge much faster, okay? It's not, and there is some of the papers, most of the papers that claim about the initialization that could give you an idea about you could initialize, for example, at a point that is very close to a local minima. These are not, they don't have solid theoretical background for these theories, and at the same time, they don't prove that empirically. So usually, it's a better idea not to waste your time trying to initialize at a point that is close to local minima, but or the global minima if there is any, but try to initialize in a way that you have healthy gradient. So this is the target of the initialization. You just don't want, for example, to initialize in a saddle point or initialize your network to all zeros or so on. Okay. Then you will try to overfit one batch and check your model variance through the training error. So when you try to check, overfit one batch, at least you will think my model now is working and it can memorize at least this one batch. This will not give you an idea about the variance and the bias. I'm talking about one batch only. One batch only, this is just as a sanity check that your model is able to have at least a memory or memorize these batches. And this will not give me an idea if my model will generalize for the entire data set, but will give me an idea that my skeleton of the training or the evaluation is not broken, okay? So this will prove that I have a loss, I can minimize it, and I can overfit a model. Then I can use a bigger model then. Visualize your tensors before and after processing in the feed-forward pass. Usually when you're having a dirty data set, you will be doing a lot of transformation. And this transformation actually could go in an unexpected way. So usually you would, for example, try to normalize across the channels, but you normalize across the batches. So, and you think you have done it well. So usually you could use, for example, Python debugger to have a look at the tensors that directly goes into the model after the pre-processing phase, and then directly goes to the model. Why? Because this will confirm that you are doing what gets into the model is what we expect. Okay, be careful with the broadcasts. This is, yes, this is a simple numpy feature, but it could screw up an entire project. Views also, if you are using views, make sure that you're also distinguish between deep copy and shallow copy. So if you have a view and you have changed it somewhere else, it could change your another view. And also the transpose that makes the information across the dimension. Generalize your code later. So you don't have to think about the vectorization from the beginning. Start as much as you can. So you remember in the interviews, it's always advisable to give the naive approach first, because it's harder to break that in the beginning. It's easy to have your code working without having concerns about vectorizing it at the beginning. So don't try to generalize your code from the beginning. ReLU is safer choice. It's compared 6 times faster than the sigmoid or tanh. Also, you could find good information about this or why, especially ReLU versus sigmoid and tanh, apart from the gradients in the Johnson Michigan Deep Learning Introduction to Computer Vision. Okay, then the last part here is initialization. Go for K-mean, better for ReLU, or Xavier, and fix-up initialization for the ResNet blocks. So the fix-up is the one that I have talked about on the ResNet blocks. I will send you these if you want to dive more about them, because we don't have lots of time. Okay, so we have so far built our data pipeline. We verified that our model is actually, our training pipeline is working, because we were able to overfit small patch of the data. Then we will try to overfit the entire data, okay? This is where we can now move freely between the models. Don't be a hero. Avoid exotic architectures in the beginning. So don't start, for example, with GPT-3, or for example, the transformers or BERT models. Try to, for example, start with something that is usually not that big. We still have, we already used, for example, small ConvNet, but you can go, for example, ResNet 16, or something that you could go for from the knowing networks. But don't go, for example, something that is proven yet to be state of the art in the beginning, and then after that you could eventually go for it. Adam is safer, more forgiving to a wider range of hyperparameters. So if you don't know about the hyperparameters in the beginning, it's usually recommended to start with Adam, because other hyperparameters, like especially the SGD and ARMS probe, they need a lot of tuning around the ReLU to get the same results as Adam. Complexity only one at once. Start with the small images and then use the big ones. Complexify only at once. Don't trust learning rate decay defaults. Your code could secretly be driving your learning rate to 0 too early. So also, yeah, I don't recommend using schedulers in the beginning. So usually the schedulers, if they don't understand the landscape of your data, or a bad choice for the schedulers or the learning rate schedulers, could kill your learning rate, or goes to 0 very early than expected. Then after you get to regularize your data, you overfit your data, you could start your regularize. I guess this is something typical most of you are doing already. You could get more data, so put a preference to get more data than further tuning on small data set. Whenever you have a way to get more data, put more effort on that. So if you have the option to use dropout or start doing any kind of other things, get more data. I'm not talking about data augmentation, like trying to, if you're doing, if you know that is someone or somehow has data on the web but is dirty, try to clean it, and that effort could be much actually valuable to the regularization than going to the other parts. Data augmentation, which is half fake or a fake like GANs. Half fake is like the transformations that we could perform in the images, like rotation, scaling, and shrinking, and so on, or completely fake like GANs. But I don't recommend this because you already, unless you have a lot of data and you are very confident with training GANs. Then we will talk about transfer learning just shortly. Stick with the supervised learning. No version of unsupervised learning has reported strong results in modern computer vision except for NLP due to higher signal ratio. So the thing is that as much as you can, it's going to be tempting, for example, to use for example, CNN in an encoder, and then deconvolution and the decoder, and then use that CNN for the classification, or build a classifier on top of that. Usually, the empirical result doesn't show that it's actually a good idea. So as much as you can, just stick to the supervised learning. Smaller input dimensionality, superior dimensions are another opportunity to overfit. So try to look at if you can drop data that you don't think are significant to achieve your task, or they are redundant, or any kind of data that you can reduce the dimensionality. I know using deep learning models feel tempting to use just to give it any kind of inputs of any dimension, but having many dimensions will actually give a bigger chance that you're gonna overfit, okay? Because you will have more scarce information on the dimensions than it's just the concept of the dimensionality reduction, that you need data points that goes exponentially as the number of the dimension to represent the same amount of data. Then after you do all of these, you could go for a smaller model. Smaller model doesn't change. You don't have to change your entire model. So you don't have to go, for example, from ResNet 150 to AlexNet. You could just, for example, change the fully connected layers, which is actually one of the main reasons to overfitting, to global average pooling layers in the end, okay? And also maybe you could try to use a smaller batch size, because we know when we are doing batch gradient descent, we are trying to actually put estimate of the gradients, and having estimate of the gradients will actually add noise to the direction of the local minima, and that's kind of regularization also on the model, but on the optimization landscape. Also dropout, we will talk briefly about it, and the weight decay, which is, I guess all of you heard about it, and visualize the learned features as well. Okay. So there are just some points to compare about this regularization also. When you are doing a dropout versus data augmentation, there are many recent papers that are talking about it's better to use data augmentation whenever you can instead of dropout, because dropout are kindly blindly reducing the network capacity. It drops neurons in a way that is not determined, and then you will not have any clue exactly how your network will converge about all of these sub-networks when you are having a dropout mask. Introduce a model-sensitive hyperparameters, and also the dropout will make your model more sensitive to the hyperparameters. So when you have a dropout, you will still have to choose the dropout rate, and also you will have that will affect, as we will see, the learning rate and the batch size themselves. So you don't want to actually have a model-sensitive hyperparameter based regularization. And this paper is actually a paper that talks especially about this. So they are comparing the performance of a different no regularization and here weight decay with dropout. So this is if I'm doing none or light data augmentation, sorry, light data augmentation, heavy data augmentation, and this is with or without dropout. So these are the different colors, and you can see, for example, heavy data augmentation in this CNN is performing much better than having weight decay and dropout without data augmentation. Yeah. Okay. So, and also there is a recent papers that are talking about, or actually this is because of the empirical experiments. Usually when people use dropout and batch norm in the same model, you will see that a model with these two will perform kind of a worse than a model with only dropout or a model with only batch norm. Why? Because the behavior is different. Dropout would shift the variance from the training to the testing, because in the dropout we don't actually use we will use different dropout mask in each iteration, and then during the test we will calculate the probability of the dropout, and then we will multiply all the activations by that. So it kind of change the variance from the training to the test. But you remember in the batch norm, in the training, we will actually accumulating the running means and running variances, and then we want to use them on the test. So this is causing kind of unstable numerical behavior in the inference, which is called the variance shift. It's kind of dropout tries to change the variance from the training to test, and patch norm will try to maintain it. There is this recent paper, which is understanding I'm not sure what is this terminology between the dropout and batch normalization by variance shift. Okay, there are just two topics before we go to the scaling part. The imbalance data sets. I guess you already, yep.
Yeah, please, we have some questions in the chat if you could.
Sorry, I just saw that. So there is a question, what we bring day 1 to unique data warehouse before generating the statistics? What if we bring day 1, day 2 to a unique data warehouse before generating the statistics? I'm not sure if I understand the question. Can you elaborate more about what do you mean by having a unique data warehouse before generating the statistics? So Abu Bakr is saying, is data augmentation limited to images, visual tasks, for example, text input and other types of inputs? No, it's a very general concept about data augmentation. It could be on text images, on even sometimes there is techniques for generating synthetic tabular data, but I'm not sure if like I remember someone has been like saying the statement that there is no techniques that you could apply easily to the other tasks that are not, for example, having visual representations or not. Because when you are doing data augmentation, especially for the classification, you want to apply kind of transformation on the sample, but you still have a condition. You want to apply that transformation in a way that you maintain the identity of that transformation. And that is especially easily can be applied in the visual tasks. But it's kind of a more tricky in the other tasks, but still there is ways and there is research on the data augmentation going on, for example, the text or the natural language itself. Okay. but I'm not that familiar exactly with it. So let's talk about the imbalance data. So for the imbalance data, we already have had the competition of cassava leaves. I'm not sure how the guys, I haven't seen the reports actually to see how the people address the imbalance in the datasets. So there is just, I'm mentioning here some of the techniques that we could use. So resampling is the naive way. We could undersample if sufficient quantity. Otherwise, we oversample. So if we have a lot of data, then we could undersample the dominant classes, okay? And that's it. You just cut off part of the data and then don't use it from the dominant classes. Oversampling is the opposite. You could, for example, apply data augmentation techniques on the underrepresented classes, okay? To make it maybe just having the same number or something closely or reasonable about the amount of samples we have on these classes. But this is the condition is about if we have sufficient quantity or not. Okay, then you could use weighted sampler. We know that in PyTorch or TensorFlow, you could have a weighted sampler that is during the training. If you are doing weighting sampler, that means the probability of getting, so it's random, but the probability of getting sample from the underrepresented classes in this batch is going higher than going higher. That means that we will actually get a sample from the underrepresented classes in a more frequency or frequency that at least equal to the upper or the dominant classes. And that is, we don't actually explicitly have more samples, but the way that we show the samples, the model is kind of biased to have more gradients that will drive the model into learning from the underrepresented samples. The k-fold cross-validation, instead of just splitting the data into small chunk of validation. So I remember I was asking some of the students, have you done the validation during the training on the Cassava competition? Most of them didn't do it because they felt that the data set is actually small. And that is true. So in such case, if you think that if you're gonna take from the validation, you could do k-fold cross-validation, which is actually your model get to see different parts of the data, and still the validation will not affect the entire amount that the model will see at the end. And then this is also a small trick, which is binarialized model. I guess this is you could introduce this on the loss function that you will define in PyTorch. You will have to define a special function. In Keras, in TensorFlow, you will have the weighted class, class weights. So class weights, that means you will actually try to send a gradient or a weight multiplied by the gradient equal to inversely proportional to the rate of the number in that class. So usually for the small classes you will give a higher weight, and for the bigger classes you will or dominant classes you will give a smaller weight, and that's kind of will you will still have unbiased data, unbiased sampler, and so on, but the model will have larger gradients or larger information from these few samples than the big or the dominant classes. And this is very easy trick, but it's actually one of the most preferable tricks that works fine out there. And also watch for batch norm. I don't know what's the solution for this, but there are studies that have shown that batch norm usually puts the bias in the majority class. Why? Why would the batch norm bias our model into the majority class? Because during the batch norm, we calculate the normalization parameters, which is the mean and the variance from the batch. And the batch is most likely to have more data from the majority class than the underrepresented. So that is kind of unfair, and that is going to bias the training because we keep this statistics running. Okay, but I'm not sure how we're going to. This is actually a question. If someone finds the answer for it, I would be happy to address it. Okay, so for the hyperparameters, this is most of you are knowing it. Usually when you're training, we're gonna use schedulers. The schedulers is just timely decreasing the number or the learning rate, and it just kind of there are many of them. The cosine is one of the preferred out there because it has less additional hyperparameters, and you could do manual tuning, and we could see that just in a few slides. For gigantic models, you might need to warm up. So there is a message from Abubakar: if the degree of imbalance is the same in training and validation and testing, the resampling may result in lower scores if we are trying to win a Kaggle competition. Is this correct? I don't have empirical evidences, I would say. I'm not sure of the answer. If the degree is imbalance is the same in all of the data sets, you would have robust results. So if you are doing training, you would expect your model to perform the same on the validation and the test. Oh yeah, now I understand the question. So if you're saying if the test and the validation themselves are not balanced, then it's better to keep it without resampling. I would agree from practical point of view, yes, but usually when you want to have a model, you want to evaluate it on balanced data sets. So it depends on the Kaggle competition and you're working on. So if the people are keeping data set on the target that is also unbalanced, and the data there is not actually, so the dominant classes is still the majority, you will still get a pretty good performance, not just but it's not because your model is performing better in all of the classes, rather than your model just chose to neglect having good performance on the underrepresented classes. Yeah, so I would say it depends on if you have the Kaggle competition people using balanced data sets on the validation and the testing. But your question, yes, you're right about this. So the hyperparameter search resists the idea of doing manual search. Usually when you're doing, for example, Colab code, and then it comes to the hyperparameter search, you want to change the learning rate, you want to add layer, you want to change things together. So this is kind of feel tempting. Let's change the learning rate and start training, and then you just gonna wait and watch it. And this is kind of tempting. So try to avoid this feeling. You're gonna waste a lot of time if you don't invest time to design hyperparameter search pipeline. That means you will learn, have a predetermined set of values for these hyperparameters and then do the search on them. Especially when you start, for example, working on a scalable way and you have a good compute, then you want to design a script actually to generate these models trained on a different hyperparameters. And you know, we already did this together, the grid search versus random search. Also, some of the students when I was talking to them about the Kasafah challenge, they were looking at how high the model were going for their accuracy or the loss. And that was, yes, that is good. You want to see that. But you also want to see how the model was progressing with time. You will not know what is wrong with your models without looking at the learning curves. So this is very important. And usually if you don't look at real time, if you don't see this at real time, for example, in TensorBoard or any kind of other logging modules, you would just be waiting and looking for numbers that is not that informative about what is going wrong with your model. So I would highly recommend that you look at the learning curve as your training is going. Don't look just at the final numbers. You will not know what's the best step to go for. And this is from also the course from Michigan. You could see that the loss here, for example, weren't going down unless we spend a lot of time. That means there is a bad initialization at the beginning if you have something like this. If you go down and then it flattens, that means that your learning rate is high, and then your optimization is overshooting around the local minima. You need to reduce maybe the learning rate. If your modeling was already going down and then you change the learning rate and then it goes flatten, that means that you decay too early. So you don't decay before it flattens like this in a plateau. And then this is where it comes to the overfitting. We know that the validation and the training curves will diverge at some point. Here it's if they are going up together with a reasonable gap, this means that you're doing well. Just keep training and give it time, give it time, give it time. Don't just look at one epoch or two epochs and then judge your model. For this learning curve here, this is actually I remember I had trick with kind of this learning curve. This one looks more tempting than this. This one. So you see, these are two going up, and here also they are going up, but the gap here is a small gap, not necessarily, but usually mean that your model is underfitting. Underfitting means that it's not actually reasonable that your model is performing as good as the same in the validation, which is samples that he was never trained on, or it wasn't trained on. Okay, so if it wasn't trained in the validation and it performs very close to the training, then you're probably underfitting, and then you will reach at a point. So underfitting, no matter how you do, you will not get a better performance after you reach the saturation point, because your model has no capacity to move to go for further feature extraction. And this is why make sure that this gap is kind of reasonable at the same time. This sometimes looks tempting, but this is not always happening. Like, I'm not saying it's necessarily that this is underfitting, but usually it happens a lot that it does underfit. So Kobe, you're saying, so could it be a bug if the learning curve doesn't appear to be changing, but the accuracy is high after all? Yes, it could be a bug, or it could be, unless you're doing transfer learning, but yes, it's if the accuracy is far from 1 over the number of classes, then you would try to suspect something. So when you're trying to learn, looking on the learning curve, what do you usually do? You could log the losses in the using Matplotlib or any kind of any visualization tool, or I recommend that you want to look at this learning curve at real time. So you want to have a visualization center, and this is why you would have TensorFlow board, and this is regardless if you're working with PyTorch and TensorFlow, there is a good way to integrate TensorBoard easily with PyTorch. You could use weight and biases, 1B, or CommitML. I personally prefer weight and biases, and it's you could train your model locally or on a server or anywhere else, and you could just use few lines of code to log everything that you wanna log in the cloud. You could log images, you could log losses, you could log any kind of data that you are actually looking for. So I recommend, and it's free. And I actually logged projects that takes more than around 300 gigabytes, and it's still free. They haven't charged me yet, unless I find it, and they don't need a card for that. What you can do more, you could do model ensembles. I don't want to talk about this more. And then we have transfer learning and fine tuning. So we know also most of the people in the competition, they have done on the Cassava competition, they have done transfer learning. But some of them are saying that how many layers we should tune or fine tune. Should I tune only the classifier part, or that's kind of question. So I would say there is just kind of a rule of thumb. It's not always generalizable, but it works in most of the time. So transfer learning and fine tuning, when should I do what? So transfer learning, I'm saying that you're taking the same model, you're throwing out the classifier part, and then you inject the classifier at the end of this model, and you only train the classifier. You don't train the feature extractor part. Okay, so if you have a CNN, you just AlexNet, you could throw the other or the last two fully connected layers, and then run maybe SVM or average pooling, global average pooling at the end. So this is transfer learning. Fine tuning, I mean, like, you still take the same model, but you are back propagating or updating even the learned model parameters. So if I have a large and a different data set, so let's say our model is trained on ImageNet, okay? And then we had this cassava leaf data set. Let's say if the cassava leaf was very large, okay, and is it a different or the same data set? So we wouldn't say that it's actually different, but it's also not the same. Not the same in the sense that we have 1,000 classes in ImageNet. Yes, that is a big number of classes, and the model have seen different kind of data, but the model wasn't trying to discriminate between two different species. Two different leaves from the same species in a plant. It's trying to differentiate between or distinguish between a cat and a dog and a boat. So the kind of discriminative features that are learned by that model is not actually the same as what you will model learn in the cassava leaf. That's how you can judge it's different or not, okay? And that's, if it's large enough, sometimes you could train model from scratch because you have enough data and it's different. But it's also recommended to fine tune. Like, it's an ImageNet, and it's also different from what kind of discriminative features that my model would learn, but it's also recommended to start with ImageNet model because the weights that is already learned in the first layers could be actually internal representation that is also going to be learned eventually by the same training that you're going to do. And that will help you to converge faster. So if it's large and similar data set, then you also can fine tune the model. So it's if ImageNet and you still have, for example, image and cat and dog, then this is apparently two different species that discriminative features are already there in the learned features. Small and different data sets. So if my data set is small and different, then I can just fine tune fewer layers. Because if it's a small, then I will not have enough data to learn the representation for a deep network. And if it's a small and similar data set, you don't have to fine tune. Don't fine tune any layer, just plug in the last classifier and then tune that classifier. Okay, so this is our 4 different scenarios on the table that somebody could go for it. So I don't think we have a time for this, which is actually the original talk was about distributed computing. I wanted to talk about how I can use multiple GPUs and the different strategies that I can use with the different GPUs. There is also the talk about the DevOps. which is a lot of the things that usually you do from the using Docker containers, using the scalable training or distributed training, and also wanted to talk about big data. I just could give one line of code in the distributed computing. It's just that you have multiple GPUs. You're lucky, you have multiple GPUs. You want to train your model, and then you wanna send your model to train in the same time, like faster. So the thing is that there is different strategies when you are doing distributed computing. One of this is the model parallelism. Model parallelism means, like, if, for example, have a ResNet, you could have part of the weights in a one GPU and part of the weights in another GPU. But this is inefficient because you will have to wait sequentially for the updates. Data parallelism is that your model actually will be replicated in different GPUs. It's the same model, okay? But you will this instance will, for example, take the first batch. This is the second. This is the third, and this is the fourth, fifth, sixth. So each time we change a batch, we actually we performed a 3-batch update instead of 1. And this is now it's called the mirrored strategy, and you could do this when one line of code in actually 2 lines. Yeah, 1 line of code in TensorFlow, and then just define your model in a scope in Python. So you could just send the model, but there is another things that you want to consider, which is exactly the same things that Georgia talked about in the last slides in the first lecture. So when you're doing this, you will actually aggregate the loss from different models in this model, and this will have larger gradients, which means that you are actually using a batch size which is 3 times the original batch size. And when you change the batch size, you're usually going to change the learning rate. So Georgia is talking about this in details in the lecture, so I recommend to go for it. For the DevOps, that means it's just there is some paradigms that we need to make so this part is about deploying our machine learning models after we achieved a good accuracy. We have a clean data, we have a good data pipeline. We want to deploy some of them. So if your data is actually is much larger than, for example, 100 gigabyte, then you cannot fit this data in a single RAM. This is where it's you want to need, for example, to try to use multiple instances. You will use multiple machines, and that will make it harder to deal with this all logic unless you are a DevOps engineer. So there is these tools like Hadoop and Spark, which help us to process these big data in details. Hadoop is mainly 2 big components. The Hadoop distributed file systems, which is a way that we use to distribute and store the data in a distributed infrastructure, okay? And at the same time, the other component is the MapReduce. MapReduce is the way that Hadoop is using to process this distributed data. So this is how it's stored the data, and this is how to process the data. MapReduce. Probably you heard about MapReduce a lot. We don't have time to go through this example, but I would happy to go for it after that. I wanted to talk about Hadoop file system as well, and then we will have Spark. So the difference between Spark and Hadoop, they are both performing on big data, but they have different purposes. Usually people compare Spark versus Hadoop, but that is not correct. Usually when you compare them, you will compare Spark versus MapReduce, because Spark is the processing part. Spark core engine could use data that comes from Hadoop distributed file system, or the format that Hadoop is using, or it could use this from different multiple sources. So Spark is not against Hadoop, it's against MapReduce, okay? And the difference between them is Hadoop is using disk to store the data and process them on disk, but this is Hadoop. And Spark are using actually the data to be distributed on the RAMs. So that's why Spark is actually could go 100 times faster than MapReduce when it comes to real-time processing. This is actually very good comparison that I spend a lot of time to get all of these points, but we don't have time. This is comparing the performance between Spark and Hadoop. And this is the cost if you're working on infrastructure. And this is the data processing. So still Hadoop is there. Hadoop is not a dead project because Hadoop is used for batch processing. So let's say that you have data that is residing in hundreds of gigabytes in disk. You could use Hadoop to process this data easily. Spark is usually used in real-time processing. So if you have iterative algorithm, which is like machine learning algorithm, you have the model on the memory and the data on the memory, and you don't want to send the data between the memory and the disk. Okay, so if you want everything to be in the memory as iterative algorithm because the machine learning, we're performing many batch steps if every time we calculate the loss and then back propagate and then update and so on. So this is iterative. You don't want to perform a step, store the data on the disk and then pull it again. This will take a lot of time. That's why Spark is usually most famous with machine learning algorithm than Hadoop. Hadoop is if you want to do kind of extracting analysis from the data on batch and so on. It's good because you're gonna pull the data, you're gonna perform an operation, and then it will go back to the disk again. When you do again another operation, it will go from disk to disk. So that is the main difference between batch processing and stream processing. Fault tolerance, don't want to go into these details. There is just, this is the last slide. So there is another component which is called Apache Beam. Apache is the one who's behind actually the two Hadoop and Spark. But the thing is that they recently have released Apache Team as one of their main components or main softwares, which is very easily integrated actually inside TensorFlow. There is actually TensorFlow.Apache Beam, which is you can use the streaming capability of Apache Beam inside your code without even going to read about Spark and Hadoop. Okay, so this is for you guys if you want to do big data things. Big data, that doesn't mean that you're not doing deep learning. You're just dealing with data that is not going to fit in one RAM even if you have multiple GPUs. So you want to coordinate this together, but you want to do it on Apache Beam. Sorry, you want to have something to take the burden of doing this by yourself. There is comparison between Spark and Apache Beam here, which is, I think, very good. If you want to go, I will complete these references and send you the slides. Sorry, I think I took a lot of time. That's it, and we're done. Okay, so if you have questions, otherwise we could go back to the.
Okay, questions. If you have any question.
Yeah. So Emmanuel, I think. Oh, sorry. Manuel, you're saying Hive or Pig. These are all parts of the Hadoop ecosystem. So you can see here Hive for ingesting data into the Hadoop file system. If you want to pull data, ingest data, perform analytics on this big data, there is many components that rely on Yarn and the Hadoop distributed file systems to access the data, ingest the data, or pull data, or analyze the data on the way that is stored in Hadoop file system. So there is many components that you can find, and also you can see here Spark Apache and Spark machine learning library. So in the ecosystem of Spark, they have all these three. Usually, if you're gonna work in a Spark by itself, you will work with the machine learning library from Spark here. Okay. I don't think we have another question. Okay.
I think there's no more question, and
Yeah,
it's
I'm
so
sorry I
unfortunate
have
that
taken much time than expected.
no problem. It's so unfortunate that we couldn't cover the perhaps most interesting part, but
Yeah,
I'll gather some
but I will send the slides and the
we have.
references for people who wants to do further reading.
Yeah. If we have enough people who are most interested in this part, we could take it again, take another
Yeah,
session, and you
sure,
explain them
sure.
again.
And I'm here to
Yeah, I think Francis has a question, right?
Francis. Yeah,
Francis,
I'm not sure I'm familiar with the focal loss. Is there anyone familiar with that? Can answer the question? I'm not sure actually. I'm sorry. I don't know about